Hello, everyone, and welcome to our Fellows Public Talk series. I'm Claudia Rizzini, the Executive Director of the Radcliffe Fellowship Program at Harvard University. Before I introduce the speaker today, I want to encourage everyone to submit their question. You can do so by using the Slido link, which is posted here in the room on my side, and in the chat feature on the Zoom webinar for our online audience. We encourage you to submit your questions at any time throughout the talk, and we will address them at the end of it. Thank you. It is my pleasure to introduce Tracy Slatyer, our Edward, Francis, and Shirley B. Daniel Fellow. The story of dark matter begins with a perplexing observation. Galaxies are rotating much faster than they should be. Based on the visible mass of stars and gas, these cosmic whirlpools should be spinning at unraveling rates. Yet, they remain intact, held together by dark matter, a sort of invisible scaffolding for our universe's structure. As an astrophysicist, Tracy works to understand the enigmatic mystery of dark matter and build new tools to illuminate the deeper history of the cosmos. Dark matter is invisible and undetectable. Everything we know about it has come from studying its gravitational interactions with known particles. Tracy's research focuses instead on other ways dark matter might interact, and the potentially visible radiation created from these encounters. During her year at Radcliffe, Tracy plans to study how the next generation of experiments to measure cosmic radiation will tell us more about the interactions of dark matter and enable new ways to test dark matter physics. Results from these studies have the potential to predict the formation of new black holes and chronicles our universe's history. The Q&A portion of the public talk today will be moderated by Ralph Klessen, who is Professor of Theoretical Physics at Heidelberg University, and Elizabeth S. and Richard M. Cashin Fellow at the Radcliffe Institute this year. And now please join me in welcoming Tracy Slatyer.
Well, thank you very much for the very kind introduction. I'm very honored to be here. So I want to talk to you today about work that my group has been doing and the work that I hope to do at Radcliffe, but centering around this question of whether dark matter interactions could reshape the early universe. But I understand that most people here don't spend all their time thinking about dark matter, so I want to begin by kind of unpacking this and first talking about what do we mean by dark matter, what do we think we know about it, and why do we think that? The process of how we get to what the statements about dark matter that you just heard in the introduction are sometimes a bit of a black box, so I'm going to try to open that box. Then I'll say a bit about what we mean by dark matter interactions and why we're interested in searching for the non-gravitational interactions of dark matter. And at the end, I'll talk about an example of a way in which these interactions could change the early history of our universe. Since this is the day before Halloween, you will see appearing through this talk my personal favorite kind of dark matter, i.e. my 3 black cats. So, introducing and Callaghan. So in this first part of the talk, we're going to try to open up the box, see what's inside. All right, so we're going to begin with a little bit of a historical overview. The place where, as far as I'm aware, the word dark matter was first used in a scientific paper, albeit in German, was back in the 1930s when a guy called Fritz Zwicky was just trying to measure the mass in a cluster of galaxies. That was the Coma cluster. This is an image on it on the right-hand side. And Zwicky wanted to answer this simple question of how much mass is there in this system of galaxies. Now, obviously, you cannot, unfortunately, take out a set of scales if you want to measure a galaxy cluster. How would you do it? Zwicky's idea was we'll do this in 2 different ways so that we can cross-check the answer that we get. So method 1 was a census method, a counting method. It was to look at this image, say, right, how many galaxies are there in this image? Let's estimate how much mass there is associated with each of those galaxies. Let's add up the numbers. That gives us our total. Method 2 was instead to say, okay, like census is good, but sometimes the census misses things. We know that gravity is sourced by mass. The gravity of an object depends on how heavy it is. And the gravitational pull of mass on other objects affects how fast they move. So we can look at how fast these galaxies are moving. That will tell us something about the strength of the gravitational pull that they are exerting on each other. And we can reconstruct from that how much mass there is in the system. All right? So method 1 is counting, method 2 is gravity. So he did both these calculations and unfortunately found that the answers, or fortunately for us, found that the answers are pretty different from each other. The second approach gives a number that is several hundred times higher than the first approach. So that could imply a couple of things. It could imply that something is wrong with your gravitational calculation. Maybe gravity behaves in a way that we don't expect, but Zwicky thought the simpler explanation was probably just that the census is missing some stuff. And he called this stuff that the census was missing dark matter, where in this context he just meant matter that doesn't glow. It doesn't shine like the galaxies. It's not lit up, so it's easy to miss. At this point, he was not, as far as I can tell, thinking about some kind of fundamentally new particles. He was just thinking about, it could be burnt-out old stars or gas that isn't shining. But he called it dark matter. So there were other people besides Wiki who had made observations like this around the same time, but this issue that galaxy clusters seem to have considerable mass that wasn't really showing up if you just looked at the galaxies just sort of hung around as a puzzle in the field for several decades. The next major development in the historical record was when people started to look at, as we heard in the introduction, at how galaxies rotate and how stars and gas clouds rotate around the center of galaxies. So we're going to show a little cartoon movie here. The way you should think about this is that this big yellow blob at the center represents the bright central region of a galaxy where most of the stars are, most of the gas is, and we would naively think most of the mass should also be there. That's where most of the visible matter is located. And then each of these little dots is going to represent a star or a gas cloud or another astrophysical object that is rotating around the galaxy, just like planets rotate around the sun. Now, if you know how planets rotate around the sun, you might know that the planets closer into the sun go faster, and the planets further out go more slowly, which again is just a result of the effect that the sun's gravity is stronger closer in. So similarly, what we would expect, we'll turn this on, what we would expect is that if you were to look at how these objects were rotating, close into the center, you'd expect them to be rotating pretty fast, but far out, you would expect them to be moving pretty slowly. But when you actually measure how fast they are going, when you actually measure how fast they are, just trying to get this to play. What you actually see is that these distant objects are rotating just about as fast as the ones close to the center. All right, so that's surprising. That tells us, so there are a couple of possibilities here. Again, this suggests that gravity is stronger in the outskirts of the galaxy than you might naively have expected. So again, a couple of possibilities here. It could be that our model for how gravity works is wrong. Maybe gravity just doesn't fall off as quickly as you would expect towards the outskirts of galaxies. Or the other possibility is that there's more gravity out here because there's more mass out here. So if that's the case, it tells us not just that there's extra mass in our census that we're missing, but that it's distributed differently than this bright stuff at the center. There's more of it in the outskirts. So in that scenario, you would have a picture like this, where the bright center of the galaxy is like the spiral of our Milky Way, shown in this image, but it's surrounded by a much larger cloud of invisible matter that we cannot see. Okay, so that's interesting. That suggests that if we go with the dark matter hypothesis, where now dark matter is just meaning something that we cannot see, transparent matter might actually be a better word. Unlike my cats, we don't think that this matter is dark or opaque or absorbs light. We really think that light goes straight through it, which is why we can't see it. But this would suggest not just that this extra matter is there, but it behaves differently from the visible matter in some significant way, which explains why they're distributed differently. Now, just a little diversion. So we could ask the question of, right, like, how do we tell these hypotheses apart? That's an important question. There's, I think, a little bit of guidance to be gained from just much older studies of our own solar system, because the way that we initially discovered Neptune was not by seeing it directly. It was through its gravity, was through its gravitational pull on the orbit of Uranus. People noticed that the orbit of Uranus had some funny features which were not well explained by our current theories of gravity or our current understanding of the solar system, but they realized that if there was an additional planet out there, its gravitational pull on Uranus could explain the discrepancies. They made a prediction for where that extra planet had to be. People followed up with telescope observations back in 1846 and found Neptune where it had been predicted. So in that sense, Neptune was dark matter when we first discovered it. It was something that we had measured only by its gravitational pull and had never seen. So the kind of dark matter that Zwicky talked about, the kind of dark matter seeing in these the way that we might be seeing in those rotation curves, is something that in a sense you can say we've discovered it because we've seen its gravitational pull. When we talk about discovering dark matter today as a goal, usually what we mean is doing the equivalent of those people with telescopes looking at Neptune to be able to perceive it or interact with it directly. So a lesson from the solar system is that gravity can be used to discover things that are otherwise invisible. We should not be super skeptical about the possibility that we can learn about new objects that we didn't know about before purely by seeing their gravitational pull on visible matter. That said, the solar system also has a bit of a cautionary tale in that there was another planet that had a weird orbit that we couldn't explain with the physics known at the time, and that was Mercury. And people spent quite a bit of time trying to say, oh, maybe Mercury's orbit is weird because of extra matter in the inner part of the solar system. And it turned out that in Mercury's case, that was not the right answer. The correct answer was that we needed to upgrade from Newton's theory of gravity to Einstein's theory of gravity. So the solar system both has examples of we really can use gravity to detect stuff for the first time, but also examples of, but sometimes it's a clue that your theory of gravity is wrong. So how could we tell them apart? So one of the challenges in telling dark matter and modified gravity apart, so where by dark matter now I'm just using the hypothesis that there is some additional matter here, we're seeing its gravitational effect, even if we can't see it directly yet. The difficulty is that matter gravitates, dark matter gravitates, so they'll be drawn to each other through gravity. That means that in the regions where there's a lot of matter, we would also expect there to be a lot of dark matter, and vice versa. The distributions aren't exactly the same, but they're going to be correlated in that sense. So you might think that, so what we would like to do is to be able to separate the dark matter from the ordinary matter. But that's not naturally going to happen if you just leave them out in the universe because they'll be attracted to each other. But what you can do is look for systems, for special situations where the two types of matter could at least be temporarily separated. So you want to look for some kind of cosmic filter. Now, anytime I have a filter, like say I'm filtering solids out of a liquid, what I'm relying on is that the two substances to be separated have different properties in some way, right? Like liquid can go through my sieve, solids cannot. But we have reason to hope that the dark matter and the ordinary matter has different properties because we know that the ordinary matter collapses into spiral disks, and whatever is explaining the behavior of these stars at large distances from the center of the galaxy, it does not appear to be collapsed into a disk. If it was, then the rotation measurements would look different. So one hypothesis that you might have for explaining this difference is that turns out to work is that if we know that dark matter feels gravity, but if the only force it feels is gravity, if it doesn't feel electric and magnetic forces, then you can show that in that case, dark matter would make these kinds of puffy clouds around galaxies, while the ordinary matter, which does feel electric and magnetic forces that we know about, would collapse down into this disk. And then based on that hypothesis, you can think about, okay, what are situations that would filter the dark matter from the ordinary matter, where the fact that the ordinary matter has electric and magnetic interactions and the dark matter does not would become important? And the answer to that, which led to a fairly spectacular discovery a bit under 20 years ago, was to look at areas where galaxy clusters are colliding with each other. So let's talk about what happens to the ordinary matter in this case. So galaxy clusters, they contain stars, they contain galaxies, they also contain clouds of gas, mostly hydrogen and helium gas, some of the other elements. If you push two clouds of gas into each other at high velocities, they will exert pressure on each other. They will heat each other up. This is like trying to compress gas. They will heat each other up. If they heat each other up enough, those gas clouds will start glowing in X-ray radiation. But that pressure, that heating, that emission of X-ray radiation, all of that relies on the electric and magnetic interactions experienced by ordinary matter. So for dark matter, we might not expect that to happen. So this is a picture of the famous system called the bullet cluster. These are stars and galaxies in the background. These red regions are showing are a false color image of the gas clouds associated with two clusters that have just collided with each other. And we get this measurement by looking at these gas clouds glowing in X-rays. So it's called that you can see that this gas cloud over here has a distinctive shape. We think it has that shape because it just went through this other cluster. And the analogy is that if you shoot a bullet through water, you get a similar shape here, again, due to the interactions of the bullet with the water. Okay, so that's what the visible matter is doing in this case, where two galaxy clusters have collided. But if there were also large clouds of dark matter associated with the galaxy clusters containing most of the mass, as suggested by Zwicky's observations, what would you expect those to do? So it's again a cartoon. So each of these blobs is going to represent a galaxy cluster. Red is going to represent the ordinary matter. Blue is going to represent the dark matter. The red matter is going to behave like we just described, where they collide with each other, smash into each other, slow each other down, exert pressure on each other. But we're going to assume that the blue clouds only interact via gravity, have no electric and magnetic interactions. So if this was the case, then when these clouds collide with each other, the red clouds will slow down, heat each other up and glow, but the blue clouds will just keep going. So that will lead to a situation where the blue clouds are out on the edges and the red clouds are more towards the center of the collision, and the red clouds are also deformed by the interactions, whereas the blue clouds are more unaffected. So at the end, we went from the cartoon to the real image of the bullet cluster. Again, the red is the gas clouds. So what is the blue? The blue is a measurement of where the gravity is strongest in this region. So this was done by astronomers Clow et al., 2006. Part of the team was based just down the road at the Harvard-Smithsonian Center for Astrophysics. So what these blue regions are showing here is a measure of where the gravity in the cluster is strongest based on the bending of light from the stars in the background. Gravity bends light, so you can use that as a measure of the strength of the gravitational field. And you see exactly what you would have expected, that this collision does seem to have acted as a cosmic filter, that these two, that these red regions are closer to each other, but most of the gravity, most of the apparent mass in the clusters is actually coming from these blue regions. So this was one of the major observations that convinced much of the field that we really are looking at some kind of matter as opposed to gravity, because while you could have modifications to gravity, it's pretty hard to understand how, if this was just a modification of the gravity of these gas clouds, why the gas cloud is over here and its gravity is over here. All right? Even if we might, whereas if this is two different kinds of matter, this collision has filtered one from the other, it makes sense that they can be separated. There's a newer set of observations that is in a similar vein, where we see some galaxies that seem like they have hardly any dark matter. Again, that's easy to explain. If the dark matter is just a new component, galaxies can collide with each other, their dark matter clouds can get stripped away, but it's somewhat hard to explain if dark matter is really just a code word for gravity of galaxies. It's hard to see how a galaxy would lose some of its gravity. Okay. So if we interpret this result this way, then it also gives us another piece of information, which is that if the dark matter interacts through electric and magnetic forces, they need to be much, much weaker than the electric and magnetic forces that ordinary matter feels. They might not be completely zero. You can't say for sure that there are no interactions for the dark matter. But if the dark matter has interactions other than gravity, either with itself or with the ordinary matter, they need to be pretty small. So the dark matter does have to be different from ordinary matter in this sense. Okay, so that's a large number of the pieces of the puzzle. But in the last 20 or 30 years, we've also gotten another set of information, which was not at all what Zwicky first envisaged in the 1930s, but has been a really powerful probe both of how much dark matter there is in the universe and a very convincing argument that, at least to me, that something like this dark matter story is correct. So these are observations of the cosmic microwave background radiation, which is sometimes called the Big Bang afterglow. So let me say a little bit about how we think our universe evolved. We believe that our universe began with a hot Big Bang, And ever since then, back when the universe was once much smaller, much denser, and much hotter. And ever since that time, it has been expanding and cooling down. We have observed radiation that we believe was emitted when the universe was only about 300,000 or 400,000 years old. When we map that radiation over the sky, it looks like this. This is a picture taken by the Planck telescope of the European Space Agency. So what is going on in this image? So this is a snapshot, a picture of what the universe looked like when it was only a few 100,000 years old. Today, it's over 14 billion years old. So what we think this baby universe looked like, it was a hot, almost perfectly uniform sea of light and protons and electrons and neutrinos and presumably also dark matter. I'll tell you why we think the dark matter was already there in a minute. It was almost perfectly uniform, but not completely. There are ripples in this sea. And so when you look at this image, these red and blue regions are showing where this sea was a little more dense or a little less dense at those early times. The scale of these fluctuations is at the level of 1 part in 100,000. So it is almost perfectly smooth, but there are just little waves on the top. So we can measure those ripples really, really well with instruments like Planck. One way that we often analyze them, you can show it holds almost all the information in these ripples, is to basically study how intense are these little waves as a scale of their scale of how large they are. So like how much variation is there over sort of a scale of, in like a patch of this size versus a patch of this size, compared to how much variation is there on much smaller scales. And an analogy for this is that when you have harmony in music, you have a bunch of different, you can have multiple notes that have different pitches and different intensities. So you can disentangle, okay, which notes did I have, which pitches, which intensities. So that's the same kind of analysis here. We're asking, okay, how much power is there in these ripples as a function of their size? And it turns out that those ripples can tell us a lot about the properties of that early sea. So this lower panel here is showing the result of doing that analysis on the map that I just showed you. Do not worry about the exact details of what the y-axis and x-axis are, but schematically the y-axis is telling you about intensity and the x-axis is telling you about wavelength or frequency. So high scales here are like high-pitched notes. Okay? They're short distances, small fluctuations. So we see this very distinctive pattern in the ripples. And it turns out that we can predict that pattern, and it tells us something about how much of the matter in the universe felt just gravity versus gravity and also electric and magnetic forces. So why is that? Let's suppose we start out at some time, we have an almost perfectly uniform sea, but we have one region that is a little more dense than the other regions. What's going to happen? Well, if the only force around was gravity, if I have a region where there's a bit more matter, it'll have stronger gravity, okay? So that region will tend to attract other particles towards it, and the density will go up in that region. So we'll have a growth in the wave there, a growth in regions that are already more dense. But if I try to cram a lot of charged particles and radiation into a small volume, what do I get? I get a pressure, right? Try to squash them down, it exerts a pressure. That pressure reduces the density. So the combination of these effects, of gravity on one hand and pressure on the other, leads to an oscillation, causes these waves to oscillate. So by measuring their properties, we can in some sense just get a measure of how strong was gravity relative to this pressure coming from electric and magnetic forces. And if you do this calculation just assuming like all the matter experiences electric and magnetic forces, that corresponds to this. So this thing up the top that is oscillating is showing how this pattern of ripples would change as you change the amount of matter in the universe that experiences only gravity but not electric and magnetic forces. So when this purple bar is at its lowest, that's what this curve should look like if there was no dark matter in the universe, if all the matter felt electricity and magnetism. As we dial up this purple bar, that increases the amount of matter that feels gravity, but not pressure. So it changes the balance between gravity and pressure in these oscillations. And it turns out that to get the right answer, I don't know if I can pause. Yeah, I probably do not have the skill to pause it at exactly the right point. But it turns out that you get a result that matches this data really accurately over thousands of data points here when there's an amount of dark matter in the universe that is about 5 times the amount of ordinary matter. Where again, dark matter here is now defined as stuff that feels gravity but doesn't feel electricity or magnetism the same way as ordinary matter. Okay, so that is, when we say 80% of the matter in the universe is dark matter, this is where it comes from. Just from understanding, like, we turn this knob of how much dark matter is in the universe, what do we need to get the properties of these cosmic ripples right? There's a follow-up that we can do to this, which is, so I told you that was the radiation from when the universe was only 300,000 or 400,000 years old. But those ripples actually serve as the seeds for formation of all the structure that forms in the universe at later times. So eventually, some of those regions of high density, they grow ever more dense over time. And detailed simulations of this process have shown that what eventually forms, under the assumption that, based on what we just said, that 80% of the matter in the universe is dark matter, what forms is this filamentary web-like structure of dark matter stretched through the universe with some regions that are higher density than others. And those high-density regions become the cradles of the galaxies, because ordinary matter is gravitationally attracted to regions of high dark matter density. The gravitational pull of the dark matter draws the ordinary matter there. And in those regions of high density, gas can collapse, form into stars, and the stars form galaxies, and eventually we get systems like the solar system with planets and eventually people. So when we look out at the night sky, when we see the stars and the galaxies, in our current picture of the universe, all of that is drawn on and supported by an invisible scaffolding of dark matter, of transparent matter. And we can predict, based on our theoretical models of the early universe, under the assumption that what's there is dark matter just gravitationally interacting, we can predict the shape of this scaffolding really well and predict the distribution of the galaxies really well. And it agrees extremely well with detailed observations that we have. With there is one extra assumption you need for that to be true. If the dark matter was rocketing around the universe at close to the speed of light, it would not form this filamentary cosmic web. These structures would just dissolve as quickly as they formed. So you only get a prediction like this if you add the extra requirement that the dark matter is pretty slow moving. So long as it's going much, much slower than the speed of light, it doesn't matter. You don't get a good measurement of exactly how fast it is going, but you can set an upper limit on how fast it can move. That, incidentally, tells us that neutrinos are not the dark matter, or not all of the dark matter. Neutrinos are particles that we know about. They're very light. We've measured them in various telescopes. But through the formation of this cosmic web, they would be very fast-moving. And so they can be at most about 1% of the dark matter. OK, so this brings us to a point where we have this puzzle. There appears to be this extra matter component in the universe. We can, we can use it to make predictions of how the universe should be structured that appear to agree extremely well with observations, provided that it has weak interactions other than gravity, is slow-moving in the early universe, and that it's been around at least since the universe was 300,000 or 400,000 years old. But that is enough to tell us that we don't have an explanation for this stuff. So again, just to come back to what do we mean by dark matter, so it should be clear at this point, all we mean by matter is that it exerts and experiences gravity. That as far as gravity goes, it's just like ordinary matter. That's what the matter means there. By dark, what we mean now is that if it interacts with light and with electricity and magnetism, it does so very weakly. But we also kind of mean, the word dark is often used in our field to mean that we don't really understand it. It's unknown. It hasn't been illuminated. People use the word dark in the context of dark energy in this context, which is an energy component of the universe that we don't understand, and which I'm not going to talk about now. But dark matter, thus, it doesn't mean a specific scenario. It doesn't mean maybe dark matter is some new kind of particle. It could be. We don't know. But really, all that dark matter means is a placeholder term for this puzzle, for what appears to be a gravitating component of the universe where we don't know what it is. But we have some restrictions on its properties. Can't interact too strongly, was already present when the universe was very young, was slow-moving when the cosmic web was forming, and we know about 0 particles that have these properties. So that's the puzzle. That's the big question that I and many other people are trying to answer. So now let me go on and say a little bit about how you might do that. So, dark matter interactions. My cats interact a lot. They are not nearly as weakly interacting as dark matter is. But even if sometimes they ignore each other for a long period of time, they might have occasional encounters. And that's what we hope might be the case for dark matter, that even if its interactions with electricity and magnetism and other forces are weak, it might have occasional encounters that are not purely governed by gravity. Well, why do we hope this? So, I told you that there is this great puzzle of dark matter. If you give particle theorists a puzzle like this, something like this happens. I say this is a particle theorist. So I do not want you to understand every word that is on this slide. I'll just go through, but there are sort of 3 takeaways that I will give you. So everything within this red blob is a class of ideas for what dark matter could be. Not even a single idea for what dark matter could be, a category of ideas. Everything outside the red blob is a broader idea for how physics could behave once you go beyond the standard model of particle physics that we usually think about. So for example, there could be new symmetries of the universe. Those of you in the Fellows program, Melanie told us about symmetries a few weeks ago. So there could be new fundamental symmetries of the universe, like supersymmetry, that relate to the dark matter problem. The universe could have more dimensions than its usual 3 space dimensions and 1 time dimension. That could be related to the dark matter problem. The Higgs boson in the standard model that we discovered a bit over a decade ago could be related to the dark matter problem, or it could be related to neutrinos, or to enduring puzzles related to the strong interactions that hold protons and neutrons together. Dark matter could even tell us something about new forces that the standard model, that we do not experience, that ordinary matter does not feel, in the same way that dark matter does not appear to feel electricity and magnetism, while we do. Dark matter could be could be just like the first example of many new particles, and it's the one that we learned about first because it's the most abundant in the universe. So that's one point. Particle physicists are really excited about dark matter, partly because this is one of the most striking examples we have of a place where our current theories just do not seem to work. They just do not explain something. And if we can figure out what it is, as well as answering this question of what is 80% of the matter in the universe, it could potentially be a key to unlock other possibilities, to study other problems on which we don't have a lot of other observational handles. That's it. So that's the optimistic takeaway. The takeaway 2, these are all viable possibilities for dark matter at the moment. These ideas are all possible explanations for why you would have a component that makes up 80% of the matter in the universe but has so far only been found by its gravitational interactions. They are not distinguishable by the data that we have in the present day. So the problem here is not what are the can I come up with an idea for what dark matter could be? We have tons of ideas for what dark matter could be. The problem, the difficulty is, how do we tell which one of these is true? Or if any of them are true. I mean, it might be that the right answer is not on this slide. So one answer to that is to say, well, let's try to measure the distribution of dark matter better than we have ever measured it before. Let's continue to measure like smaller and smaller galaxies, get more and more detail about that cosmic web. Maybe that will allow us to distinguish these hypotheses. That's a good idea. That's a major avenue of research. I'm happy that they're doing it. But it is unfortunately true that for a lot of the ideas on this slide, their gravitational footprints will be completely indistinguishable for any experiment that we could imagine doing in the next century. So we should keep doing this, because there are definitely possibilities where the gravitational footprint looks sufficiently different that you could find it tomorrow. Right? And if that is the case, we'll immediately be able to eliminate all those possibilities that look the same, and we wouldn't be able to tell them apart in 100 years. So we should do that. But we should also keep in mind that it might not work. Like, it might be that the true answer is in this category that looks a whole lot like a lot of other dark matter models. Okay, so that is one of the major motivations for let's try to look for interactions that are not gravity, because the space of models that I talked about on the last slide often does make extremely different predictions for how dark matter particles would interact beyond gravity. So by interactions, these could be particles bouncing off each other, these could be particles colliding with each other and destroying each other, these could be one particle decaying into other particles, anything like that. And if we were to detect one of those interactions, that would immediately let us eliminate almost all the possibilities. Even when we don't get a detection, even when we just get null results, that's still a powerful way to rule out categories of scenarios. Okay? All right, so there is a big worldwide experimental search for such interactions. My research falls within that search, but is definitely not exclusive. So I just want to tell you in my remaining time about one category of interactions and how it might affect the early universe. Okay, so an example of what I might mean by an interaction is it's possible in many of these dark matter scenarios that if two dark matter particles collide, they could destroy each other and produce visible particles that we actually could look for. So these could be any of the particles we know about. They could look like radiation. So from our perspective, what that would look like is particles and radiation popping out of nowhere. Okay? I mean, really, it's coming from the dark matter. But if we can't see the dark matter, it would look like it just appears from nowhere. So this would look like a violation of energy conservation. So if that had happened through the universe's history, if through the universe's whole history, occasionally just like particles pop into being from nowhere, that would have changed how our universe had evolved and developed. So let's talk a little bit about, so now we're going to talk about this last bit, reshaping the early universe. I did not take this photo specifically for this talk. I took this photo back in the pandemic when I was teaching a class on the particle theory of the early universe, and this cat was a good teaching assistant for Zoom classes. All right, so what could this kind of interaction, this kind of trickle of energy do to the early universe? Well, let's first just talk a bit about what budget we have to work with, how much energy we have to work with. So we measured earlier that there's about 5 times as much mass in dark matter as in visible matter. That means that for every atom of hydrogen, there's 5 atoms worth of mass stored in dark matter. Now, Einstein told us that E equals mc squared. I said there was no math in this talk. I guess there is one equation, but it's E equals mc squared. So we can say, so that means that this mass in dark matter is a store of energy. So we can ask how much of the energy in the mass of a hydrogen atom would it take to do something to that hydrogen atom? Suppose I wanted to heat up the hydrogen atom by 10,000 Kelvin, 10,000 degrees above absolute zero. I guess that's somewhere more than 20,000 degrees Fahrenheit. That only costs 1/billionth of the energy stored in the mass of the hydrogen atom. So if you had 1/billionth, so if you took 1/billionth of the energy stored in the dark matter, spread it out among all the hydrogen atoms in the universe, you would heat up the whole universe by 50,000 Kelvin. Right? So there's a lot of energy in the dark matter. Similarly, if you wanted to break a hydrogen atom is made from a proton and electron circling each other. If you want to break them apart from each other, that costs about 1 in 100 millionth of the mass energy. So again, take 1 in a billionth of the, take 1 in a billion of the energy in the dark matter. That's enough power to break half the hydrogen in the universe into protons and electrons. These are big dramatic effects. If they happened, we would definitely have noticed. If dark matter had heated up the whole universe by 50,000 Kelvin, we would know. So this tells us that this is going to give us sensitivity to a very small fraction of dark matter undergoing these interactions. This is why we can hope to see this, despite the fact that I told you earlier that the bullet cluster tells us that dark matter doesn't really interact very well. Okay, so my group has worked on a number of ways in which these effects might manifest themselves. I'm very happy to chat about them later in the question session or just in discussions here at Radcliffe. So I just want to show you one example in the last few minutes of the talk, or two examples really. So you might ask, if the universe was getting heated up or we were breaking apart the hydrogen and helium, how would that affect the epoch in which the first stars formed in our universe? This epoch is sometimes called cosmic dawn because it was the first sunrise in the universe. So how we think these first stars form, and this is actually a case where my colleague Ralph Klessen knows much more about it than I do. I am just a particle theorist, but I will give you the outline. How we think the first stars form is that when you have a cloud of hydrogen and helium gas, you want this cloud to collapse in on itself to form stars. In order for this to happen, the cloud has to be able to cool down, because otherwise, we said earlier, when you compress gas, it heats up, there's a pressure that causes it to expand again. So the cloud needs to be able to dissipate its heat in order to collapse. what we think is the major coolant at this early time is actually molecules of hydrogen as opposed to atoms of hydrogen in this gas cloud. Hydrogen molecules are an excellent coolant, and I'll say more about this. I'll do a little foray into chemistry on the next slide. So having more hydrogen molecules helps. The presence of that coolant allows the cloud to radiate away energy. It fragments into a bunch of little clouds, and then in these individual little clouds, some of them can collapse and form stars under certain conditions. So my group already in previous work studied how energy transfer from dark matter through the interactions that we've talked about could inhibit or enhance this process. And it could go either way, actually. On one hand, the first thing that we thought was, oh, surely this is going to slow down this process, because if you're heating up the universe by a lot, if you're heating up the gas clouds by a lot, they'll have more heat to dissipate. It will be harder for them to cool down. So that will make it harder for them to collapse and fragment and make stars. So that was our first guess. But it turns out there's actually another effect which we found for dark matter scenarios that are not already excluded is generically the more important effect, which is that having the energy injection from dark matter lets you make more molecular hydrogen, and molecular hydrogen is a great coolant. So the reason that this works, we'll just do a little bit of chemistry here, is molecular hydrogen is most easily formed in the early universe by having free electrons around. So my cartoon here, I start with a hydrogen atom, and the green dot is an electron. They can join up to make a hydrogen ion, a negatively charged hydrogen ion, and radiate off a photon, which I'll indicate by a particle of light, which I'll indicate by this yellow dot. But then, once I have this negative hydrogen ion around, if it encounters another hydrogen atom, then a common thing to happen is that these two form molecular hydrogen, so H2, and the free electron goes flying off. So the free electron is acting as a catalyst in this process. It doesn't get consumed, but its presence means that you can convert atomic hydrogen into molecular hydrogen. And then once you've got the molecular hydrogen can vibrate, it can jiggle, it can rotate, and that serves as a store of energy. That can convert energy that's stored in the heat of the gas into these little vibrations, and the molecular hydrogen can emit light that carries away this radiation. So this is the molecular hydrogen cooling process, and basically the more free electrons you have, the more efficient this process is, and the quicker the gas clouds can cool. So, and as I told you, energy injection from dark matter can break apart hydrogen atoms into protons and electrons. So the more energy injection you have, the more of these free electrons you have. So we had to do a balancing calculation between, okay, how does this play out between you're heating up the gas on one hand, but you're giving it more coolant on the other hand. Turns out that for stars, usually, at least at the level of our quick calculation, usually the cooling wins. I've been talking a bit with Ralph about ways to follow up on that and to explore this in more detail. But there's another question that is interesting, which is, okay, so suppose that's the story for the first stars. What about the first black holes? And there is a lasting puzzle about the first black holes. So in the standard picture, the way that we form black holes, which are regions of space from which even light cannot escape, is that when a star reaches the end of its lifetime, if it's sufficiently massive, it can collapse down into a black hole. So you start with the star, you get a black hole, and then that black hole can grow over time, either by merging with other black holes or by gobbling up matter from its surroundings. So then the black hole will grow and get larger. But it can only grow at a certain rate. Like if you start with something that is, about the mass of a star, not that much heavier than the mass of the sun, there's a limitation as to how fast the black hole can grow by gobbling in matter and by merging with other black holes. And you can estimate how big this could be. And then you can compare it to observations. And there's a bit of a gap here. We observe in the very early universe really large black holes, much larger than you would have expected from this picture. And I mean, most recently, this come from data from the James Webb Space Telescope, but this has been known as a problem for 20 years. It's just been made more sharper recently. So one possible solution is to say, well, maybe you don't need to make little stars first, make little black holes and then have them grow up. What if we could start with a much larger seed black hole to begin with? So in particular, I told you before that the picture is we have this cloud, and it fragments into a lot of smaller clouds, and then they each make stars. What if instead of that, we could have a large fraction of the original cloud collapse into a big black hole, either directly or by forming a lot of stars that are so close together that they very quickly collapse into each other, or by making a megastar and then having it collapse? So that idea is called direct collapse black holes. The original proposal goes back about 20 years. One of the people who worked on this, Priya Natarajan, was also a Radcliffe Fellow, so this idea has a long history with Radcliffe. And so the question is like, so how do I get this? How do I prevent this fragmentation? Their original idea was that if you have radiation from a nearby galaxy that breaks up all your hydrogen molecules, that destroys your coolant, then the cloud will not be able to cool down and fragment very fast. It will just sort of slowly cool down and can eventually collapse into this large object. So a question that I'm interested in looking at this year is the degree to which energy injections from dark matter could change this picture. So again, as with the stars, you can imagine it could heat the early gas clouds. There can be extra radiation from this kind of energy transfer. The radiation coming out of nowhere could also break up the molecular hydrogen, the coolant, but also the free electrons mean that you're making more coolant in the first place. This has already been studied in a couple of specific models where people found like specific examples of dark matter scenarios that could affect this process. I want to just do a somewhat more systematic study, really understand what the space of possibilities is and which dark matter scenarios realize them. You could imagine that there might be cases where there are some dark matter scenarios that would just completely prevent direct collapse black holes and other scenarios that would predict that you have tons of them. So that's, again, there are a number of different ways in which dark matter could affect the early universe, but affecting this population of early black holes is one that I'm interested in looking into. All right, so I'll stop there. I and my cat will ask for questions.
So, thank you, Tracy, for this wonderful and highly insightful introduction to one of the most enigmatic questions we have, I would say, in modern science. That about what makes up the very fabric of the universe itself. And this work at the interface of astronomy observations, astronomical observations, theoretical astrophysics, but also bringing in lots of insight from the particle physics community is, I think, what is exactly needed to make progress in this field that has, I would say, puzzled us and the community and many other people for decades, and probably will continue this way. Let me jump right into the key question here, right? You alluded it in some sense by your very complex cloud picture. There were axions, primordial dark matter, there was this and that, supersymmetry and so on. So if you were to bet, let's say, 1 year of cat food, where would you place it in this complex picture? What is your gut feeling? Where should we search?
I think my cats would be very angry at me if I suggested betting 1 year of their cat food. But yeah, so it's a good question, and part of my answer is that I really don't know what the right answer is, because I really do think that there are lots of plausible, well-motivated possibilities. There are lots of possibilities where if we found out tomorrow that one of these was the right answer, I'd be like, oh yeah, seems reasonable, makes sense. The problem is just that we have a bunch of possibilities like that we don't have the ability to distinguish. If you forced me to bet, and the bet had to be pretty specific, like I had to say, okay, I want to pick this particular candidate, I would probably bet on a particular candidate called the QCD axion, but partly that's just because it has a very well-defined target region. Like, there's a well-defined test that you can do, and you can run the test, and either it's there or it's not, and you know more or less what mass scale it should be at, and you know more or less how strongly it should be interacting. That's not a test that we've had the ability to do experimentally up until very recently. But recently, the experiments searching for this kind of dark matter have gotten a lot better, in part due to developments in quantum sensing technology. And so now I think we really do have a prospect of testing that particular class of dark matter models in the next decade, if we can actually fund and build the experiments and if they perform to expectations. So, if you made me bet, I would probably bet on that, just because it's a pretty well-defined target. So that the advantages there are, it's a pretty well-defined target. It would solve multiple problems, like not just the dark matter problem, but another problem as well, and is something that we could test in the next 10 years. But I would not be even slightly surprised if it turned out that the answer was something different.
Well, there's a long history of that dark matter candidate, like supersymmetric things, that have turned out not to be, really valid candidates anymore. But maybe just a quick follow-up question for the non-initiated. What is an axion?
Right. I am not going to give the full answer to this question, but I will give a rough answer to this question. So an axion would be a new particle that is extremely light, much lighter even than neutrinos, which are the lightest particles that have mass that we know about in the present-day universe. It would interact, it would have electric and magnetic interactions, but very, very exceptionally weak ones. I mean, it would easily be consistent with all of these bounds that I have talked about on the electric and magnetic interactions of dark matter. And the reason why people originally proposed the axion is that there is a puzzle in the strong interactions of the standard model that hold the constituents of protons and neutrons together, where if we just do our best estimate of our current theories, if we take our best current theories for these interactions and we try to estimate, for example, how a neutron should interact with electric and magnetic fields. Now, you might say, oh, but a neutron doesn't have any electric charge, so does it interact with these fields at all? And sure, it doesn't have any electric charge, but it does have charged components within it. So you would expect it to interact with the electric field at some level. We can make an estimate for how strongly it should interact with the electric field. And then we actually do the measurement, and we have not found that interaction, and we have set an upper limit on how strongly the neutron can interact with the electric field in this way that is about 10 orders of magnitude lower than what we would have naively expected. So there's this just question of the neutron is made up of charged particles. We have really good evidence for that statement, even though it's overall neutral. Why isn't it interacting with the electric fields? For the experts in the audience, this is through the dipole moment. Why doesn't the neutron have an electric dipole moment? And it turns out having a new particle like the axion could answer this question. It would essentially say, well, there could be a particle, similar to the neutron that had an electric dipole moment, but through its interactions with the axion, you would essentially erase that electric dipole moment. It would lead to the particle that you see having zero observational electric dipole moment. So that's the context in which it was first suggested, and then people realized that if this axion was sufficiently light, it could also explain the dark matter. So, but maybe, but it could also be that these two problems are not connected to each other. There could be an axion that solves this problem with the neutron electric dipole moment, but doesn't solve the dark matter problem. That's a perfectly possible possibility. But or it could be that the solution to this puzzle with the strong interactions doesn't involve an axion at all. It involves something else.
So, in a sense, the search for dark matter, both on the elementary particle side and on the astrophysics side, is both looking for the needle in a haystack, but on the other hand, we talk about the elephant in the room, right? Because it dominates the mass budget. But there is another elephant that is even bigger and even more enigmatic and darker. And you mentioned it twice. Dark energy, which causes the universe to accelerate at an increasing speed, which is weird in a sense, and asks for new fields, for new approach to fundamental physics. And so I was wondering, how do you see the relation between, these two elephants, the dark energy, the dark matter, if there is one at all?
Yeah, so I used to tell people before I got tenure that the reason I was working on dark matter, not dark energy, was because I felt it was a much easier problem, or potentially a much easier problem. And the reason that I am thinking a little bit more about dark energy these days, but the reason that I would say that is that with dark matter, we have, we don't know exactly what the dark matter is, but we have this very simple hypothesis that is just some kind of matter that we haven't found yet, that our census of particles has missed, and that seems to work really well. I mean, it seems to describe a huge amount of data to really high precision, and this doesn't require any revision of the foundations of particle physics or how we think about the universe. It just requires that there's some particle that we've missed. So in that sense, it seems like there could be a solution to the dark matter problem that is easy. in some sense. It's just like, oh yeah, this is a particle like other particles that we understand. It could also be tiny black holes left over from the early universe, but it could be, it more or less behaves like other objects that we understand. We just haven't figured out exactly what it is yet. But dark energy doesn't feel like that. I mean, dark energy, I think there is much more of a consensus in the field that we really, really do not understand what is causing it. We don't even have like a self-consistent theoretic. The situation is not like dark matter, where, as I said, we have tons of ideas that are viable and seem well motivated, and you can make a good argument for it. Dark energy, I think, just looks really weird in essentially every framework that we have for physics beyond the standard model. So it seems like there is a higher chance there of it really requiring some revision to the way that we think about physics at a fundamental level. Whereas, I mean, the other thing is that we just have more experimental handles on dark matter. Like, we can measure where dark matter is through its gravity. With dark energy, we've basically got one number, maybe two numbers, if you're lucky.
And only the universe as a whole is an experimental ground. But this leads to another question that I think needs to be asked in this context, and that is also something that has been raised at least twice in various forms in the questions of the audience. What if you're really wrong, right? Yeah. What if the current dark matter or dark energy paradigm is not right? And there are quite some of our colleagues who say maybe we should really seriously think in that way. There is modified Newtonian dynamics which can explain the rotation curves, but not many other things. However, this field of research has become quite sophisticated in the last 20 years. So what is your stance on this?
Yeah, so I mean, on one level, as a particle theorist, I would actually be very happy if the answer was something, the answer to the dark matter puzzle turned out to be, some modification to the way we think about gravity, in the sense that that would be much more interesting than just having some extra particle that we haven't found yet, but that otherwise fits very neatly into our idea of how the universe works. It would be a bigger conceptual advance if something like that was true. That said, I mean, I laid out for you why I think most of the field has come around to this really looks like a new matter component, not a modification of gravity. Like, we might be wrong. It's always good to think about alternative hypotheses, but I'm glad that people are still working on the idea that this could be some modification of gravity, but the examples that I have seen, some of them quite sophisticated, which try to write down a modified gravity theory that explains dark matter, still end up invoking a new field or fields that behave exactly like dark matter for the purposes of cosmology, because that cosmological data is so good. Like, those measurements of the ripples in the cosmic microwave background and then the subsequent cosmic scaffolding that forms through the universe, they're really good, and it really just looks like another matter component. So at the point where you're saying, right, well, to replace my explanation for dark matter, I will invoke a new field that behaves exactly like dark matter cosmologically, to me at that point, you have, but again, because I'm not wedded to any particular explanation for dark matter. To me, dark matter more or less just means something that behaves like matter in terms of its gravitation, but doesn't have other interactions. And so there's a lot of space in there, but if it's a field that looks just like dark matter cosmologically, I don't know if there's really a meaningful distinction between that and what I call dark matter.
We have many additional questions in the chat. However, in the remaining 1 or 2 minutes that we have, let me ask or summarize a number of questions that all revolve around the question of precision measurement. And that is, in a sense, a good follow-up on what you just said, right? How can we sure we measure the right thing? You mentioned the microwave background, the cosmic microwave background. You mentioned the expansion velocity of the universe. You mentioned the bullet cluster and Zwicky's work that is now 100 years old, so to say. How
and actually, his original calculations were quite wrong. It was somewhat a coincidence that he did at least find the right direction of the effect.
So, are we precise enough to make statements? What is your opinion on that?
So I think different measurements have extremely different degrees of precision, which is another reason why I find it unsatisfying to see people suggesting alternatives to dark matter that only explain the behavior of galaxies but do not explain cosmology. The measurements that are both most precise observationally and for which we can make the most precise theoretical predictions are the ones related to those ripples of the cosmic microwave background radiation and to the structure of the cosmic web on large scales. Once you get down to much smaller scales, you're dealing with systems like those gas clouds that have collapsed into stars. There you have a lot of subtleties, as you know extremely well, Ralph, in terms of what is the ordinary matter doing? Once these electromagnetic interactions come into play, you can have supernovae shooting huge amounts of matter out of the centers of galaxies. The timing and level of star formation really matters. It can shake up the gravitational potential. It can redistribute the dark matter. And so making precise predictions becomes much harder at that point. And the way that we do it is that we try to run large scales, we try to run huge computational simulations. But there are a lot of uncertainties in those models because there's quite a bit about how the universe evolved at late times that we don't understand. So there really is an issue. I mean, there are some observations that don't look exactly like the simulations. And then you have this question, okay, is this reflecting that there's either something wrong with my dark matter hypothesis or that I need some interactions beyond gravitational or that my dark matter needs to be fast moving? Is it reflecting that either there's something wrong with the dark matter hypothesis or that I need a variation on the dark matter hypothesis? Or is it just reflecting that there are a lot of uncertainties in the simulation and I haven't modeled the universe well enough? And I think at that scale, that's a really good question, and the answer the field has come to at the moment is more or less, yeah, we don't trust the precision of the measurements enough to be able to say that these discrepancies are important. We need to keep working on making the simulations better, as opposed to spending a lot of time thinking about how we would, people do think about trying to explain those discrepancies, but you talk to people who do the simulations and they're like, yeah, I don't think we've nailed the uncertainties. But at large scales for the cosmic microwave background and the large scale structure, there I think we've got pretty precise measurements and we've got a precise theory and they agree really well with each other. So there's a lot less wiggle room. And so for me, going back to these questions of modified gravity theories, for me what I want to see is a modified gravity theory that explains those cosmological observations without having to invoke a new field that behaves exactly like dark matter cosmologically. And then I would start to be like, oh, that's really interesting because dark matter fits the data well, but that doesn't mean it's the unique hypothesis that fits the data well. There could be other things, and that would be exciting to see. But some of these scenarios really only focus on trying to explain data in a region where our predictions are way less precise, and that I find less interesting.
So thank you, Tracy. I think it became abundantly clear there is enough work to do. And I think we are all very happy and grateful to be here, to be given the time to focus on these important
Absolutely.
Questions of how the universe is made up, how it has started, came into being, and evolved. So thanks again for your highly interesting presentation, sharing your insight with us on this really important topic of modern astronomy and astrophysics. I also want to talk the audience, you here and online, for highly interesting questions. Apologies that we could not cover all of them, but there will be probably other possibilities and opportunities to ask them. So I hope you are all able to join us again for the Radcliffe virtual programs. We continue next week, and you can find all about next week's and future programs, and of course the past events and the recording of this presentation at radcliffe.harvard.edu. So thanks again for joining, and have a good rest of the day.